right, so the assignment 4 was posted on Friday, this past Friday, and it's due on Friday, the 26th. So, does anybody have any questions on it so far? I'm not necessarily expecting anything at this point, but has anybody gotten started on it, and do we have any questions? All right. So at this point, really everybody should get started on it. We've covered images and pre-images. Discussions on those. So 1, 2, 3, and 4. That's all the material there for those problems. So really, you should get started on those as soon as possible. So that you can work through any issues you might have with enough time before the due date. So last time I gave you a problem, another exercise on images to consider. So let's take a look at that before we go back to our lecture. So last time, I asked you to look at the following. So you have a function f from the domain to the range, and so let f be a function from domain to range, and a and b subsets of the domain. So we're looking at f of a minus f of b, the image of a, minus the image of b, and the image of a minus b. One is a subset of the other, but not necessarily the other way around. Okay, so it was either the image of a minus image of b is a subset of image of a minus b, or the image of a minus b was a subset of image of a minus image of b. One of these is true and one of them is false. So we want to take the statement that's true and prove it, and take the statement that's false and give a counterexample. Anybody figure that out? Which is which one was true, which one was false?
The second case
Is what?
false.
Is false. The second case is the false one. The first case was true. So, all right, so prove the one that's true. This one is true. Let's prove it. And this one is false. Let's provide a counterexample. By the way, compare this to the thing about intersections. Remember, set subtraction was a lot like, I mean, it's definable in terms of intersections and complements, right? Compare this to the one about intersections, right? There was the image of A intersection image of B and the image of A intersection B. Which one of those was a subset of the other and which one wasn't? Wasn't necessarily. Do you remember with intersection? So, by the way, this contrasts with the fact that, and it was the other way around, it was f of A intersect B was a subset of f of A intersect f of B, while f of A intersect f of B is not necessarily a subset of f A intersect f B. Was that? I'm sorry. I think I. Let's see. Am I getting it backwards? Right, here it is. Right. Consider f from domain to range, and A and B are subsets of the domain. So we proved that f of A intersect B is a subset of FA intersect FB. And then the counterexample for the other way around, right? Here's a function with domain and range, right? And we use these arrows to indicate, which domain element goes to which range element. And we let A and B be these two sets here. So A intersect B was empty set, is the empty set here. All right, so the image of A intersect B is just the empty set. However, the image of A intersect the image of B has stuff in it. Right, so image of A intersect image of B is not contained in the empty set, of course. Right, so here it's the other way around, right? Right, with intersection, this one was, the situation was reversed. And remember, A minus B is equal to A intersection B complement. So even though it's defined in terms of intersections, the fact that complement is there, it changes the outcome. It's kind of neat. Okay. So let's give a proof. So here's the proof that FA minus B, FA minus FB is a subset of FA minus B, or image A minus image B is a subset of image A minus B. So how do we do that? First sentence of this proof. What's the first sentence of the proof?
Let Y be an element of image A minus image B.
Exactly. And yeah, I mean, normally you would say X or something, but, since we're talking about something in the range, let's call it Y. And something in the domain, we'll call it X. Oh, by the way, what was the definition of image? So let's just write it down. So we've got it sitting in front of us, just in case we forgot what it was. So given a function f from domain to range, and A is a subset of the domain, right? The image of A is defined to be what? It's the set of all what? What was that definition?
F of x such that x is in A.
Right. The set of all f of x such that x is in A. And, pictorially using this sort of universal bubble type diagram, if this is A right here, A orange, if that's A, right, then f of A is just everything that A goes to under F. Stuff outside of A may still go. I mean, there may be an element outside of A which still goes in there. X is not in A. It may be that there's stuff that still goes in there, and that's fine. Let's see if I can make that look nicer. So Z not in A, but stuff that's not in A may go to stuff that's not in the image of A as well. All right, so stuff that's outside of A, it might go into the image of A, or it might not. But it's f of the image of A is the set of all f of x such that x is in A. All right, so let's do this proof now. Let y be an element of the image of A minus the image of B. So let's get a whole new page. So what does that mean? So in this expression, the last operation of this expression is set subtraction. So what does this expression mean? Y is an element of image A minus image B. Thus, right, so it's not a statement primarily about image. It's a statement primarily about set subtraction. Right. First, you apply the image operator to A, and then the image operator to B, and then lastly, you do set subtraction. So this is really something about set subtraction. It's not properly an image of something. Right? So let Y be an element of the image A minus image B. Thus, what? Y is an element of
the image of A
mm-hmm.
and not an element of the image of B.
Right. Or Y is not an element of the image of B. So now we're talking about images here. Because Y is in the image of A, what? Because Y is in the image of A, what does that mean? Right, there's the image of A right there. So an element Y in the image of A looks like what? It looks like this, f of x, where x is in A. Right? So by definition, there is x in the domain, x in A, such that
Y equals f of x.
Y equals f of x. All right. So Y is an element of A. So we're just looking at the fact that Y is an element of the image of A here. Right? And that tells us there is an x in A such that Y is an f of x. However, Y is not an f of B. Because Y is not an f of B, is not in the image of B, what must also be true about x. is it possible that X is in B? Could it possibly be the case that X is in B? Could that possibly be the case?
No.
No. What would happen if it was in B? If X was in B, then f of X would be where?
An f of B.
In f of B. But it's not.
Right.
Yeah? So it can't be in B. So
No.
because Y is not in the image of B, we must have that ooh, we must have that X, or sorry, because Y, which is equal to f of X, is not in B, we must also have that X is not in B. I mean, if it was in B, then it would be in the image of B. Sorry, then f of X would be in the image of B. But what I wrote here isn't really a sentence, is it? You don't really... Because Y, yeah, it's not really a sentence. You have to have something. Also, comma, because... Now it's better. We must have that X is not in B. Therefore, where is X? Where does X live?
A minus B.
Yeah. Right? Which makes Y, which is equal to f of X, an element of
The image of A minus B.
yeah. That's that. So very similar to that thing about that proof about intersections, although it's the other way. It's the opposite relationship that's true. Right? When it was just plain intersection, the intersection on the inside of the function was a subset of the intersection on the outside of the function. Here, set subtraction, which is intersection, is on the outside when it's contained in that containment relation. Pretty neat. All right. So to show that the other containment is not necessarily true, is not necessarily a subset of image of A minus image of B, we do what? I mean, it could be. It could be the fact that the image of A minus B is a subset of the image of A minus the image of B, but it doesn't have to be. So when something might be true, but isn't always true, right, you don't say that is not a subset of, because it could be, it might be a subset of. You say it's not necessarily a subset of. So when something is not always true. Right, I mean, like, if you don't say horses are not white. You don't say horses are not white. Say, no, a horse isn't necessarily white, because, some horses are white. You would say a horse is not purple, because there's no such thing as a purple horse, unless you painted it or something, right? So when something is not always true, you say it's not necessarily true. All right, so in order to show it's not necessarily true, we have to do what? We have to give what? What's it called again?
Counterexample.
Mm-hmm. We provide a counterexample. With counterexamples, the simpler, the better. The more cheesy and trivial it is, the better. All right? Don't come up with an elaborate counterexample if you don't have to. Sometimes you do. I mean, counterexamples can get really elaborate. I mean, that's when the mistake is really subtle. So if someone makes like a really subtle error, you know, maybe because the counterexamples are very difficult to sort of get your hands on. Right? But I mean, if the error is more glaring, there should be a cheesy counterexample. You know, so when somebody says something that's not true, well, you know, here's a counterexample. And someone says, well, it's just too simple. It's too simple. It's up to you to make the true statement, not up to me to give you, you know, not up to me to give you the fancy counterexample. Anyway, so here it is. Here's one. So we'll just make any just sort of simple kind of thing. So here's a domain, here's a range, and I don't know. I mean, I don't have any intuition as to what's going to make a nice example. Probably don't need that big a domain. We'll just take 5 elements in the domain, 3 elements in the range. So, I mean, we want to show that this is not necessarily a subset of this. Well, one way to ensure that would be to make this empty. Image of A minus the image of B. If we made that empty and then this non-empty, you know, then we'd be okay. Right, so let's say that here is the image of A and the image of B. We'll make the image of A and the image of B the same thing, but make A and B different. Right, we'll make image of A and image of B the same thing. That'll make that empty. But we'll make A and B different. So what kind of a function could we make here? So let's send 1 and 2 to A and B. And we'll send 3 and 4 to A and B. I don't even need the 5. Alright, so we'll call this A, and we'll call this B. Alright, so let A equal the set 1, 2, in which case f of A is equal to what? The image of A is equal to what?
A and B.
Yeah, little a, little b. Alright, and we'll make b equal to the set 3, 4. And so the image of b is equal to
A and B.
little a, little b. Alright, therefore, right, a minus b is equal to what?
The empty set.
A minus b. Not image of A minus image of B. Here's A, here's B. Right, it's everything that's in A, but not in B.
1 and 2.
Yeah, 1 and 2. It's just A itself. Therefore, A minus B is that, so image of A minus B is just little a, little b again. You know, I think maybe these letters are confusing. Let's say little x, y, and z. little x and y again, or little x and y. But the image of A minus the image of B is empty set. So in this case, the image of A minus B is not. But so when you want to say not a subset, you write that, right? Not equal, not an element of, not a subset of, not less than or equal to, not less than. You always just put kind of a slash to it, right? Is not a subset of image of A minus image of B, right? Because that's empty, and image of A minus B is not empty. Okay? So tell you what, for next time, let's go back to the lecture, and then we'll set up something for next time as we're talking about it. All right. So that was discussing images again, and then we went on to pre-image. All right, given a function f from domain to range. So here's domain and here's range, and a subset A of the range. And so not in the domain, a subset A of the range. Then the pre-image of A is everything in the domain that does go into the range. Anything in the domain that's not in the pre-image does not go to A. Okay, so X not in the pre-image of A. If X is not in the pre-image of A, then it doesn't go to A. So the pre-image, it takes into account everything that goes into A. So that's in contrast to the notion of image. When you're talking about image, you have a subset of the domain, and then you look at everything it goes to in the range. So stuff that wasn't in this subset of the domain, it might go into the image of A, or it might not. In general, you would have both types of elements outside of A. But here, right, there's kind of this universal quantification built into the pre-image. It's the set of all domain elements. All domain elements that go into A. So we have this example here. Here's some function defined by this bubble diagram kind of thing again. And you let A be little b, little c here. So the pre-image of A, little b, you get 2 and 6 going to little b. And little c, you have 4 and 5 going to little c. So A is little b, little c. Pre-image of A is 2, 6, 4, 5. By the way, this f with a -1 on top, it means pre-image. It does not mean inverse function. Okay, the notion of an inverse function, we'll talk about it later, but they don't really exist in general, inverse functions. Whenever you talk about these inverse functions in calculus and pre-calculus, they're for functions that are like injections, or bijections. They're one-to-one and onto, which is what we're going to talk about next. Okay, but most functions are not that, right? And then when the functions aren't that, you can sort of like make it. When a function doesn't have an inverse function, you can make it have an inverse function by sort of restricting its domain, which is like what happens with sine and cosine. And you have the sine, cosine, and tangent. Then you have arc cosine, arc sine, and arc tangent. But you know, again, that's a different discussion. All right, so we proved that the inverse image of A, or the pre-image of A, yeah, sometimes called inverse image, pre-image of A. So this is sometimes called the inverse image of A rather than pre-image of A. So sometimes the term inverse image is used rather than pre-image. Okay, so warning, the pre-image of an element B is not well defined. The thing that you're taking the pre-image of, it has to be a subset of the range. So not pre-image of B, it's the pre-image of the set that contains little b. And little b only. In which case the pre-image of the set containing little b is 2 and 6, because here's b and here's 2 and here's 6. And that's another reason why the inverse image doesn't, or sorry, the inverse function doesn't really exist. I mean, how would you define the inverse function of b? Is it 2 or is it 6? Same sort of, like with f of x in calculus, right? You got f of x equal to x squared. And then sometimes we say, okay, well, the inverse function of that is going to be square root x. Right? But how do you know how to define it? Well, you have to restrict things. You restrict f of x equal to x squared to just the positive. Right? Just the positives. So that's x squared, and that's square root x. Right? So we say that, the square root of a number x is always positive. So you have that convention. But really, x squared, it doesn't have an inverse function because, if you're talking about the number 4, well, what's the value of, the inverse function of x squared? Is it 2 or is it negative 2? Which one should it be? Well, given the situation, the geometry here, we have this, this notion that it should be the positive number, the positive root. Right? But in general, you don't necessarily have notions of geometry and solving equations and all these other sort of side special motivations. All right. You can also have the pre-image of stuff is equal to the empty set. Like here's things in the range that don't go, that nothing in the domain goes there. So you could have the pre-image of something non-empty is empty. All right, so pre-image is much more well-behaved than image. Right, whereas the image of A intersection image of B is not equal to the image of A intersection B in general. With pre-image, it is. All right, and we gave a proof of that. Let's take another example. How about this? So let's prove that. The image, yeah. So let's prove that A is a subset of, oh no, we didn't do this yet. Can't do that one. I had an example I wanted to do. Oh, so right, in the homework it was to do this about with unions. Oh no, we can do that. prove that the image, that A, which one is it? Right. A given F from domain to range and A a subset of the domain, prove that A is equal to the image of the pre-image of A. Given F from a function F from D to R and, A a subset of the range, prove that A is equal to the image of the pre-image of A. Okay, well, first of all, what's the general outline for how to prove this type of statement? What are we trying to prove? What's this and what's this? Those two objects are what? They're sets, right? So how do we prove that two sets are equal in general?
Subsets of each other.
Subsets of each other, right? So first, let's prove this, that A is a subset of the image of the pre-image of A. So now what's the first sentence of this proof?
Would it be let X be an element of A?
Exactly. All right, let X be it's in the range, so let's call it Y. Let Y, I mean, you could call it X, it's fine. But I think it might be a little bit more, a little bit more understandable if we say Y. Because that's often the way we think about stuff, right? I mean, here's your domain, here's your range, and then here's X in the domain, and there's Y, which is equal to F of X in the range. Okay, so, all right. So now we need to show it's an element of this set. Okay, well, because Y is in A, what must exist? Or what must be the case? So Y is in the range. What must be the case?
Y is in the range.
Yeah, Y is in the range, yeah. Let Y be an element of A, which is a subset of the range.
Y equals F of X.
Y equals F of X for some X. Is that necessarily true? I mean, yeah, it could be, right? So, therefore, right, there is some X in F inverse of A such that F of X is equal to Y. All right, what was the definition of preimage? Where is it? Let's put it here so we can take a look at it. All right, the preimage of A preimage of A, it's the set of all x in the domain such that f of x is in A. Right? So if you pick y that's in A, right? Well, either there is some x in the preimage of A such that f of x is equal to y, or what? Or what? What could be the case also? Oh, I'm sorry, this is actually not true. It's the other way around. The preimage of the image of A. Sorry. The other way around is not true. We're going to give a counterexample for that. Okay. So, given f from domain to range and A is subset of R, let's prove that the preimage of the image of A is a subset of A. Okay. So, let the image of the preimage, sorry. Image of the preimage of A. Let y be an element of the image of the preimage of A. So let y be an element of this. By the definition of image, what?
There's some x in the preimage such that y equals f of x
There is x in the preimage
of A.
such that y is equal to f of x. Right, because x is in the preimage of A, what must be the case? Right, the preimage of A, it's the set of all x in the domain such that f of x is in A. So because x is in the preimage of A, we get what?
F of x is in A.
Yeah, y, which is equal to f of x, is in A. And that's what we wanted. Right? We let y be an element of the image, of the preimage of A. By the definition of image, So the image of this inner set, there is an element X of that inner set. I mean, forget about the fact that it's a pre-image at this point, but there is an element X of that inner set such that Y is equal to f of X. Okay, but because that inner set is a pre-image, right, when you take that element of that pre-image and you hit it by the function f, it goes into the set whose pre-image you're looking at, which is A. So Y, which was equal to f of X, is an element of A. All right, so we started with Y in this, and now we got that Y is in A. Now, the other way around is not true. So show that A is not necessarily a subset of the image of the pre-image of A. What do you think might be the problem here? All right, what can go wrong? Why might A not necessarily be a subset of that? Oh, and by the way, because we want to show something is not necessarily true. I mean, it might be the case that A is a subset of the image of the pre-image of A, but it doesn't have to be. So we say not necessarily true, meaning that, in order to show that, we provide a counter example. All right, so we're going to have some domain. 1, 2, 3, 4, 5, say, and range. So little w, x, y, z. Well, actually, I don't like those letters either. P, Q, R, S. All right, what's the funny thing that can kind of happen with pre-images? The problem with pre-images sometimes is that there can be subsets of the range that the domain doesn't go into. So the pre-image of something, it could be empty. There are elements of there aren't always, but there could be elements of the range such that domain elements don't go to those range elements. And that is the problem in this case. Okay, so let's say that everything here goes to P, Q, but nothing goes to R and S. So here, let A be equal to little r, little s. So the pre-image of A is equal to the empty set. Therefore, the image of the pre-image of A is the image of the empty set, which is just what?
The empty set.
Just the empty set. Right? So in this example, A is not a subset of the image of the pre-image of A. How about the other way around? So here we were looking at a subset of the range. How about a subset of the domain? So now the two sets in question are the image of A the preimage of the image of A and A itself. So now we want to compare these two sets, the preimage of the image of A. All right, let's prove the following. Prove that A is a subset of the image of the preimage of A. Or, wait a minute. Prove that, other way around, the preimage of the image of A. So let X be an element of A. Therefore what? Where's f of x? By the definition of image, by the definition of the image, where's f of x? So if x is in A, where is f of x?
The preimage?
Here A is a subset of the domain. All right, we're letting x be in A. And by the definition of the image of A, f of x is where?
In the image of A?
In the image of A, yeah. Oops. Image of A. By definition of the image of A, f of x is just in the image of A. Therefore, by the definition of preimage, what does the definition of preimage say about x? Where is x? Yeah, I know x is in A. We know x is in A. I mean, that was our assumption. Right, but because x goes to f of x, which is in the image of A, where must x also be? Right, if you had a subset B in the range, so here's B. The preimage of B, it's everything in the domain that goes into B. Right? So x, which is in A, its image, f of x, is in the image of A. Now, among those domain elements which go into B, right, all of them are in the preimage of B. So now we're talking about this being B. Right? We're talking about the image of A being equal to B. And whoops.
X is in the preimage.
The preimage of B,
the
right. Preimage of the image of B, yeah. A preimage of the image of A. Right? Here's B, but we're letting B be actually equal to the image of A. But I mean, of those things, right, that are in, of those things in the domain which go to B, we call that the preimage of B. Okay, but we're letting B be equal to the image of A. So the definition of preimage tells us that X is in the preimage of the image of A. So it's a lot of sort of notational gymnastics and just knowing what the definition is, but it's all pretty much straight from the definitions that A is a subset of the preimage of the image of A. The other way around, so for next time, give a counterexample for which the preimage of the image of A is not a subset of A. Okay, so next time we'll talk about some counterexamples to that. But think of one on your own before next time. Okay. Oh yeah, the exams I should have them done for you today. Okay. So look in your email and I'll get those to you as soon as I can. All right, everybody. Have a nice day.